Hou High School. I'm a senior right now, and I participate in Regeneron Science Talent Search. I've been working on this project for like around 2 years, probably over 2 years. I started at around the start of the summer of 2019. So essentially what I did was I looked at the knapsack problem, and I designed a quantum algorithm to solve it more efficiently than existing classical methods for solving the knapsack problem. So if you, some of you might not have heard of the knapsack problem. It's a very common problem. But you definitely know what you definitely experienced it in your life. But it's pretty common problem. It's a fundamental problem in computer science. So just imagine you have a lot of objects in front of you. There are n objects. You also have a bag in front of you, and this bag has a weight of W. Okay, and all these objects, there are many different each type. There's n types of objects, and each type of object has like some amount that's in front of you. And you're trying to, and each type of object has its own weight. Like maybe apples weigh 1 pound, right? Maybe bananas weigh 500 pounds. Like it doesn't really matter like if it's realistic or not. It's just like numbers, okay? And each object also has its own weight, own profit, like a value to it. So the apples might be $1 each, and a banana might be $600 each, or whatever. And so you're trying to choose as many of the objects as you can to put inside a bag, and to maximize the total amount of money and like value inside the bag, but not exceed the total weight limit of the bag. Now, there's going to be a lot of combinations, especially when the n gets very large. Maybe there's 500 types of objects, and maybe like each type of object has like 600 items, like 600 count. Now that's going to be a lot of combinations. And a normal computer, you can't solve that problem very quickly. You can't find the right combination very quickly. So that's why I decided to try to solve this problem by using a quantum computer, or by designing a quantum algorithm, which works a lot differently than existing algorithms than computers. All right. And so, but oh yeah, and so the multi-dimensional knapsack problem is similar, except there's gonna be a lot of different criteria. It's not just weight. So like the criteria is always like you have the number of items of each type you put in times some attribute. So the weight could be one, or maybe like the height could be one, or some kind of any kind of attribute, and you add them up, and they have to be less than something. So the multidimensional, of course, is more complicated, and currently there exists no solution to solve the multidimensional knapsack problem using our normal computers. All right. And so the knapsack problem, as I said before, it's very common in our lives. You might probably might relate to it when you're like trying to buy stuff, like buy groceries, and you have like a specific budget, but you want to like choose the most valuable ones, the ones that like have maybe like the most like nutritious food or something. There's a lot of applications. For example, Amazon, they have millions of products with hundreds of warehouses, and you have to and they're trying to optimize the efficiency of their company, and conserve like floor space, of course. And so that's a really like high, that's a large scale application of the knapsack problem. And it's they can't with a normal computer, of course, you can't solve that problem very efficiently. And so also cloud computing and online trading. And the knapsack problem is also very useful when in making new, more robust encryption systems. Because the existing encryption systems like RSA, if you ever heard of it, has already been solved by a quantum algorithm called Shor's algorithm. And so we're trying to, it can be very useful to develop new encryption systems that are not vulnerable to quantum algorithms attack. And so the knapsack problem could be very useful in developing those. And so the existing, the most basic solution to the knapsack problem is you just look at all the combinations. Of course, that's going to be very slow. So that's called brute force, and it has a complexity of O of n b plus 1 n. Right? It's not efficient. Dynamic programming is also it's a lot faster than brute force, but it's still not efficient because the complexity is nw, and w being the weight, it grows linearly. It grows exponentially with the problem size, which is n. And so the knapsack problem, the multi-dimensional knapsack problem, as I said before, does not have a solution besides brute force, which is just very basic, looking at all the combinations. All right. And so in general, just quantum computing works a lot different than on normal computers because normal computers, you have wires, right? And the wires can either be 1 or 0, and they represent bits. But under quantum computer, you might heard of this before. You probably heard of this before. Is it could be 0 or 1 or anything in between. And by having qubits being both 0 and 1 at the same time, then you can represent 2 different states. Or if you have n qubits, you have 2 to the power of n different states. So if you have like 100 qubits, that'd be 2 to the power of 100 different states that they represent at the same time. So in general, what quantum computing tries to do is it tries to perform the same action on these 2 to n different states, so that it conserves the amount of times you have to perform the action, right? So like if you had if it was a normal computer, you would have to look at 2 to the power. You have to do the same thing to do 2 to 100 2 to the 100 different states, or like repeatedly, right? But if it's a quantum computer, you can do just once. It'll do the same thing to all of them at the same time. So that we had to be able to strategically perform these gates, which are just operations on these qubits, to achieve the goals that we want to do, which is to solve a problem. And quantum Grover search is one of the algorithms, these kind of algorithms that solves problems. Specifically, the Grover search algorithm, if you have an unsorted array, if you have just like a black box function, right? And the function, it takes in inputs and of course outputs, but you don't know what the inputs and how the inputs relate to the outputs. The Grover search algorithm, if you can implement the function using a quantum using quantum gates, then you're able to find all the solutions to this problem, to this black box function, using only square root of n calls. There's a typo there apparently. It says it's O to n oracle calls. It's supposed to be O to square root of n. Well, classical search, you have to look at all the different possible input combinations, which is n input combinations, and that's going to be a lot more. So we call this quadratic speedup because it goes from n to square root of n. And so previously, one person I know, who he's a PSU PhD student at Portland State University. He's called Yivei Li. He solved the graph coloring problem using quantum computing. So I started thinking, could I solve the knapsack problem using quantum computing? So here we are. And so what I did was I designed a quantum knapsack algorithm. I abbreviated QKA, so it's easier to say. That solves the knapsack problem using quantum circuits and a quantum algorithm. All right. So yeah. So the overall procedure is so here. The middle part is Grover search, which I mentioned before. You can use Grover search to, as I said before, to find solutions to a black box function. And in my case, I designed it so that the black box function is does a particular combination of item amounts in the knapsack problem result in a profit that is greater than the previous profit. And so I designed to do that. I need to design an oracle, which is the black box function that answers the question. And by using Grover search, the Grover search, it converts and can answer using this black box function, can answer the question, which Grover search gives you one of the combinations that says yes, this combination is has a profit that is better than the previous profit that we just found. And if you use exponential search, which is basically just running Grover search over and over again, then you can answer the question, what is the best, what is the combination that gives you the best profit value, while still, of course, being within the weight bounds and the number bounds. And so by doing that, we can answer that question, which is that question is literally the knapsack problem, and therefore we can solve the knapsack problem in this way. If there's questions, then you can ask me at the end, and I'll come back here and answer. So of course, I thought of that procedure, the high-level procedure, and implemented it using the Microsoft Quantum, the Microsoft Q# language. Q, of course, stands for quantum. And so it's the Microsoft development kit. It's online. You can probably find it. Just search Microsoft Q#. And I also collaborated with Microsoft, I believe last summer, to open source the code that I wrote, the QKA, as part of their GitHub repository called Microsoft Quantum Katas. And I believe there's like at least 3,000 users and who are like international researchers on it. And so if you want to check it out, it's you can go to Quantum Katas and you try to find a bounded knapsack. That's the name of the repository. And so here's some sample code. I don't think if you have really good eyes, you could probably read that, but maybe not. Anyways, that's some sample code. And so if you can read quantum gate diagrams, this is the overall diagram for my knapsack oracle. And these mostly like they don't actually show the actual gates inside. These are just overall diagrams, right? And so they're gonna like be representative of like an addition and another addition and a comparison, and also a lot of comparisons and additions and multiplications in here as well. And so of course this is only a half diagram, because when you do a quantum oracle, a quantum circuit, when you do an oracle, you have to reverse. It has to be reversible, so you have to like do everything reverse at the end. And so of course, to make sure that I had the right to make sure I programmed this right and I thought of this right, I had to test the knapsack oracle with many different combinations. So I decided I made my own knapsack datasets, which are basically just example knapsack problems. Like maybe there's 5 objects with and the total weight of the bag is 84 and all the other attributes. And so these are some example sets that I used, and I tested all the sets with my knapsack oracle and ran them all through with every single possible value that could be represented by that could arise in these sets, and made sure that every single time the output matched our expected output and whether it was actually a valid combination. And so you might notice that some of the n are pretty small, like 2, 3, 3, 4, 5. Now, of course, when like the point of this algorithm is to try to speed things up when the numbers are very large, right? But there was a very like big limitation in that the existing simulators. I had to use quantum simulators because of course quantum computers are right now are not very common. They're pretty rare. Only like really big companies are able to like have the money and resources to make them. And so like the biggest one right now in the world it's probably like 70 something qubits, I believe. And so the quantum simulators right now, in general, they all have 30 qubits, because every single extra qubit that you add in quantum simulator is like doubling the total memory you need. So around when you get like 30 qubits, that's probably like 2 to the power of 30 bits. And so that's a lot. And it's probably like a lot of like gigabytes or terabytes. I don't know the exact number, but you can't add any more because you'd be doubling every time. And so because of that, my test sets that I could test were limited, because if you have 2 big numbers, then there's a qubit limit. The qubits are limited. So I chose these sets specifically to maximize the diversity of the sets, to make sure that that they covered enough cases to make sure that my oracle was correct. And of course, I wrote everything in C++ and Q#. The quantum parts were in Q#. The non-quantum parts were in C++. And I also decided to analyze the complexity of my my oracle, because that's important in deciding how efficient it is. And so there's a paper by Dmitry Maslov where he gives a table of like the cost, like a numeric cost of the Toffoli gate, of the X gate, and all the other gates. And so I used that metric to evaluate the cost of my oracle for the example data sets. And so there's like the cost is between a range, right? So there's a minimum cost and maximum cost. So I just analyze the minimum and maximum. So I determined that I determined formulas for how big how complex my oracle is. And so I determined that the cost for the minimum and maximum cost are both linear with n, and they're log with b, like either like log 2b or log 2b squared, which is like it's not very but the point is it's not exponential, and it's pretty small. And so and when I submitted this paper the project. I wrote a paper for this project, and when I submitted this paper to the Quantum Information and Computation Journal, the editor, it was the editor who suggested that I expand on my Oracle gate cost, which so it's here now, because he said that it's going to be very useful and very important in the future synthesis of like quantum operations and the implementation of quantum gates on future quantum computers, because you need to know how much this is going to cost, how much is feasible, and all that. And so I use that n log b as approximation to calculate the time complexity of my overall algorithm, because remember, the n log b was just the complexity of the knapsack oracle, and I have to make sure that my overall algorithm, which solved the knapsack problem, is at least has some improvement over the existing classical methods, right? And so here is a very complicated formula for the time complexity in the box. Then if you want to we can use the case that like we assume all the b's are the same, which is the bounds, like how many of each item there are, and we assume that those are the same and all the profits are the same. So we just give a approximation here, and this gives O of n square root of b plus 1 n, right? That's the simplified one. And yeah, and so this is like square root improvement over classical brute force, which is very significant. And it also shows that because W can get very large, when n gets very large, this can also be faster than classical dynamic programming, because especially in cases of low B and high W. And so in conclusion, I developed the quantum knapsack algorithm, which is the first quantum algorithm that successfully solves the knapsack problem. And I implemented it using quantum circuits. A lot of times in like quantum literature, existing quantum literature, they don't actually implement it. They just like have it, like they just write it up and have a theory. But I think it was very important to implement it, because when we were actually we had to make sure that it works and that it actually like functions the way you want to function, and test to make sure that it works. And so I submitted this, and it was accepted and published in the volume 20 and number 9 and 10 of the Quantum Information and Computation Journal. I think we should open up for questions now, probably.
Sure. So thank you, Wenjun. That was a great summary of your project. There's already a few comments in the chat here. First, was there a significant speed up in solving the graph coloring problem?
Based on what I know about Yuwei's research, I'm pretty sure there probably was. If you just search up like Yuwei Li graph coloring, you can probably read the paper yourself. But yeah, I mean, it did. Of course, compared to brute force, of course, it does have a quadratic speed up, because it works like the speed up is generally the same whenever you do use Grover's algorithm on a optimization problem. It's square root speed up. And so I'm not entirely sure whether there was an existing non-brute force method for the graph coloring problem, but I don't believe there was. Correct me if I'm wrong, if anybody finds out. Yeah, why did I choose C++ over Python? I did learn Python a while back, but I also learned C++. In general, I prefer C++, and also because I was using Visual Studio. Q# is basically like the quantum version of C#, right? So they're very similar. So if you want to use Q#, then it works best with C#, because like you can actually like the C files, like the C programs, can actually coordinate with the Q programs. Python is probably possible. I haven't done it before, so I wouldn't know all about that. How many qubits total does your example use? Which example are you talking about? Let's see. I have a lot of examples here. I have the ones that are shown here. There are 5 different examples. You can see the total qubits on the right column. Set A has 20, and B has 22, 22, 23, 29. So.
Good. Are there any other questions? Here's one. I have 2 questions regarding how scalable is this solution when we talk about computation time and possible scale with currently available quantum hardware.
In terms of, okay. So in terms of real quantum hardware, I am not entirely that much experienced with like actual quantum hardware. I mostly work with in this project. I mostly worked with quantum simulators. As far as I know, like quantum computers are not like are still being developed. They're still like I said before, they're very rare. There's only like a few dozen probably in the world, and um, so yeah, I wouldn't say expect too much with current quantum hardware. Although this could definitely like run on an existing quantum computer. I don't have access to quantum computers, so I can't really do it myself. But it definitely in the future, this has a lot of potential because we'll probably have quantum computers that are a lot more easy to make, more accessible. Maybe like we'll have quantum phones or quantum laptops. That'd be very cool to see. Yeah.
Good. Are there any other questions? All right, let's thank Wenjun again. Again, congratulations on all your success at such a young age, and we expect very great things from you.
Sure. Happy to share my project with everyone else who is interested.
Super. Okay, I'll post anything on the website. Thank you, everyone, and I'll see you in 2 weeks.
Thank you, Mark, for hosting this event.
Sure.